for extreme data management analysis and visualization at the University of Utah. His topic is big data and the scientific method. Try to stay within the 20 minutes to change. Yeah.
Yes. Put this on the table.
Yeah. Is this fit?
Don't go for that.
Oh, yeah.
So I would like to talk about big data, and some observation that emerge from the work that have been done in several years now, the Center for Extreme Data in Utah that I established a few years ago, but also emerged from experience previously at places like Lawrence Livermore National Lab, where large data was really something that was prevalent already several years ago. Now it's really mainstream. So first of all, a technical definition of big data. So big data, it's like teenage sex. Everyone talks about it. Nobody really knows how to do it. So everybody thinks everybody else is doing it. So everybody claims they're doing it. This is a very nice quote from Dan Ariely. And I like to add a positive note that everybody eventually will do it. Not talking about only by sex, but really in science, lots of people increasingly are dealing with very large data and have to deal with the challenges and the opportunities that come with that. So a few examples of where big data has been very important in our experience. So this is a case, for example, where we're analyzing a few tens of terabytes of data. That was already a few years ago. And we're talking about the trend of global warming, and typically you see this plot here that tells you how the temperature goes up. And is that type of summary of the data good enough? And in fact, there was a lot of discussion, why this goes up? Is the sun having more radiation, and therefore it's a natural phenomenon, or is human-made? So we had to go back and actually analyze the data more carefully, come up with new abstractions. In this case, do the averages only based on the level in the atmosphere. And now you can see that at the top layer, from the color map, blue means temperature goes down. Actually, the atmosphere is cooling at the top layer and is warming a lot at the bottom layer. So, and most importantly, this is already happening in the year 2000. So from historical data, it's not just projected from simulation. So this is clearly inconsistent with the notion of temperature coming from radiation from the outside in. It's really warming from inside out. If you deal with lots of data properly, you can communicate those things very reliably and in a way that everybody can understand. If you summarize too much or too little, you get information that is not really actionable and can you use properly. Now, there are other cases, for example, where we got very interesting results. This was a couple of simulations in Lawrence Livermore National Lab. Those are simulations of cracks propagating in a particular material. This is the cracks at the maximum speed that the physicists thought it was maximum possible, so the speed of sound in that material. They got simulations that were actually showing cracks going faster than that, but that's just a simulation. What do you do with that? Is that true? Is that real? In this case, actually, we're fortunate that a completely different group, like a couple of years later, found out that this was actually happening. But that poses the key question is, when you analyze big data and find a trend, how do you assess whether it's really a reality that you want to kind of deal with, or it's something that maybe it's an error and so on. And sometimes you cannot do experiments. So generally, though, there are amazing opportunities. There is the whole field of developing new clean energy sources, either cleaning up the current ones or really developing new ones. This is a massive multi-scale problem that generates massive amount of data from sensing and simulations. Huge opportunities, but nobody knows yet how to do it. We can start studying more carefully the history of the universe itself. But again, how we will deal with this massive data and how we validate the hypothesis in an environment like this, where you cannot just build another universe to test if you are correct or not. And huge opportunity in personalized medicine, how we can link the massive change in scale from the smallest to the highest of entire organs or just chromosomes and so on, and develop some delivery of medicine that are personalized. And of course, can we preserve historical artifacts and in a way that even somehow they get corrupted and so on, you still allow people to basically being able to access them and have a good fruition of this kind of information. So I would like to take a break for those examples and think about big data in relation to kind of a known felon. I don't know if you guys recognize from the picture. This is Galileo Galilei, so a few years ago. And you know, got jailed because was gravely suspected of heresy. And so fortunately, well, the case actually was quickly reviewed by the church. And in '92, actually, there was the formal excuses from the church. It's been an interesting development. So Galileo was well known to establish formally the scientific method, right? How does that work? You typically kind of make an observation, propose an hypothesis, design an experiment for testing that, analyze the results, your data, big or small, and you iterate whether that match or not. The key part of the method is my experiments reliably repeated so that you don't have to believe me because I somehow have a reputation. Everybody can validate whether a certain law is true or not and how as well is established. What's interesting is that the development of the method actually was linked to the invention of a instrument, the telescope, so that he could make those observations and tell people how to do them so that they could do that themselves and not just believe him. Now, this had been evolved after for more theoretical models, and so reality in terms of a scientific method really has been shifting a lot of how can I build a mathematical method that I can kind of extrapolate towards new direction and then keep testing more and more. Now, the new instrumentation and capability are really challenging this approach. You have a telescope like this. They don't respond to a guy thinking, oh, I want to point there and look at some data. They just go brute force and survey the whole space. And in some sense, in the hope, I mean, we're really sure, but in the hope you will find something interesting. But the science is going to be done by the exploitation of the data analytics, of course, validated by people that understand the model. So it's very different. It's kind of turning around the relationship between data collection and design of the theory. There is also massive data collection on the web. You can have millions of transactions that become data that never get erased, and they get continuously analyzed to understand the behavior of people. Massive collection of petabytes of data now from many different nations that try to do climate predictions. And of course, billions of transactions for things like Google. Again, they always leave behind a trace. So how things are evolving in terms of scientific method. The first paradigm was empirical, then more theory-based. And there are challenges even conceptually to those. Important statisticians like Bock says, well, all models are wrong, but some may be useful. And this is actually true, right? You have to understand clearly the limitation of your mathematical models I really don't like, for example, people talk about the laws of physics. Those are not laws that you violate. Those are true as long as they respond to the experiments. Some go maybe too far, claiming that those are not needed anymore, but it's definitely clearly a symptom of a trend. And now there is this fourth paradigm and third paradigm arising almost at the same time, where you use simulations as a replacement for doing experiments, because you can reach resolutions in time and space that you wouldn't be able to achieve otherwise. And then the fourth, that is really purely data-driven investigation. And really those are highly connected, although the third is really focused on simulation, and the third is much broader in that sense. So now, how do we use this, and in a way, how important it is that we get things right? So for example, we know that the Milky Way is going to crash into Andromeda, and obviously we cannot test this empirically with like a few universes and try it out and perturb the situation. The issue is that this is going to happen only in 4 billion years, so I'm not that worried that we get things wrong. But now we're looking at, oh, the climate is warming up, maybe. Now, this is going to take 100 years, and it's getting more important that we get it right. Maybe not for ourselves, but maybe for our kids. But it is touching us more directly, but you have the same challenge that you have just one event that you're trying to predict. Or you can think about investing. It's like, oh, if you get it wrong, well, you're going to be broke when you retire. So there are short-term consequences. Maybe personally this is worse. But generally you have this challenge that you have something like, for example, plutonium that was discovered only 70 years ago. How do I understand the aging process? Aging is one of the most nonlinear phenomena. And so for something that has not been around a long time, and but is being used in fairly dangerous devices, and we use them. So more in general, if you look at, oh, I build a rocket purely by simulation and data-driven processing, are you gonna get on that and fly, right? Think about it for a second. And then this is an example actually of something that was designed mostly by simulation, and it was even the fifth generation, and unfortunately this was the outcome. And it was fairly expensive experiments that in 37 seconds consumed $370 million of research, and this was only due to a software bug. A small thing, recycling a subroutine out of the 4 Ariane. So it was not really unreasonable to do that. But we rely more on this stuff, and of course you didn't want to be on that if you thought about it. So now you go back, for example, to the plutonium, which we don't know how it really works, just because it has not been around, and now because a treaty cannot be tested. How do we know that we're going to get it right, that we don't have a kind of a software bug? That I know that military is more concerned about that being ineffective, but as a civil, I'm more concerned that that's going to blow up inside the silos on this side. So this is actually one of the things that started the kind of HPC race in the last 10 years. Those are kind of the top supercomputers. You can find the list on the web. And you will, in fact, you notice that most of those are actually from national laboratories that are on the defense side, exactly because of this challenge, but then they got broader and broader. And this is actually the increasing computing performance overall. This is the top, the bottom, and the middle one. So it's not just the top that goes up. Notice this is a log scale plot, so every time you go one step up is actually multiplied by 10, the overall performance. A massive new resource that we have available. And then how do we use it, and how we can make science with that? What are the challenges? Obviously, data is becoming a major driver in investigation. And what we really know is just that having the data, it's important, but having just the data does not guarantee that you get answers. The only guarantee you have is that if you don't have the data, you will not get the answers because the information is embedded somewhere there. So you have to do more than just collecting the data. So that's why HPC computing, analytics in many forms, and visualizing, exploring the data is becoming a major component of research. And I was glad to see that in other talks that is considered a key aspect. We have done, for example, work to make data readily available in different environments. This is a case where we're doing an experiment for advanced photon source in Argonne National Lab, but the scientists were actually in Washington State at Pacific Northwest National Laboratory, and we were able to let them stream the data on the fly so that as they're renting this super expensive facility, instead of going back with a terabyte of data and finding out a week later that they were disappointed because they made a mistake, they could watch on the fly and adjust the parameters of their experiments and not just simulations. And so now we're able, for example, to deal with data sets like this. This is like a 6.4 terabyte data set. If people are interested later, I can show, like, even on a small laptop like this, I can stream it from a remote server and do interaction on the fly. And this is leading to technology that now we're looking at commercializing so that, for example, on the medical sector, they can generate data, get diagnostic really quickly, and go back and forth with the results. And it's really exciting to see this complete spectrum of from kind of mathematical research in space filling curves to algorithm to deployment to actual commercialization. Now, I've been thinking of processing data really fast. This is an interesting case from Geico where they were looking at, they cannot make quotes fast enough to respond on the phone to, given your situation, how much is going to cost you a certain insurance level. What they did actually, instead of doing this massive streaming process on the fly, they actually went around to the opposite side. Every weekend, they actually think of all possible family in the US with all possible requests. They run all the scenario. Now they have this massive database where the answers are ready. So it's cool to see actually very different directions that you go from doing things really fast or doing things kind of brute force before, and you really have to look at all possible direction. One major challenge with big data is also being able to quickly build abstractions that don't let you look at just the little details, but trends locally and globally. And so one thing that has been really important is to look at alternative of multi-resolution things where classical approaches that reduce the data, reduce the information, you kind of, in a wavelet scheme, you blur your image and at the end you don't see anything. Can we do something like a human where when you reduce the data, you go down, say, to a few bytes here and express an important concept? So here we found, for example, using topology as a complement to statistical methods that actually you can build nice structures out of data without any knowledge about the particular domain and still having the level of abstraction that typically humans deal with really better than just average and statistical summary. So instead of having a description of a whole distribution, I can actually have a network of connection. I have partition in space. And what's exciting is actually this is happening on multiple different domains, and it can be done automatically without having to go into a specialized field, whether it's molecules or medicine or porous materials, and so on. So how do you understand if you're doing things right? When you're dealing with massive data, even if you're doing it fast, high resolution, and so on. One key aspect that is emerging is this notion of having uncertainty, quantification, and verification and validation. So those are key technical word really that tells you, am I computing the right thing and am I computing it right? So for example, people not only want to understand, well, do I design a new clean fuel and therefore a combustion simulation? I want to understand the 10-dimensional space of all possible combustion simulation, and then I can look at that in this way. Think of this as a terrain in 10 dimensions. There is a big hill and 3 valleys, and the 3 valleys are where things are not burning well. Those are bad combustions, and in fact, for them, we find out that there is a condition where this combustion was needed to be avoided, and it was not simply mixing properly oxygen and the fuel. So in general, and the question is also then, are you building the software right? Can I verify that things are computed correctly with respect to the model that I have in mind? And anybody had dealt with software, you know that expecting that to be completely bug-free is not possible. There is always one more bug, as much as I like to say otherwise, I've never seen that. But more importantly, overall as a process, is the prediction I'm getting accurate, right? And now I cannot do experiments as we saw before. So, for example, this is really similar to what people do in markets. They do a model, they see the prediction, and they start trusting things that tend to be right most of the time. Well, but the reality is that in the sector where this has been done for a long time, they put you big warnings that past performance does not predict future results. And unfortunately, we're stuck with this mode just because we cannot design a few planets with different climates or different universities. So here there is a key kind of philosophical question is how do we, on this basis of something that we kind of know its flaw, still build sound science? So overall, we have seen also this aspect of we really need to build a new culture of working with big data, large teams. If I had to pick a real problem that I see in the communication among communities, that people tend to communicate tasks instead of problems. That really diminishes our ability to work together and help each other beyond what we think others can do and help them effectively. And to conclude, I see obviously this is a new era. It's very exciting. There are a number of opportunities in the things we can possibly do, new science, new engineering, new material, new understanding. As a computer science community that I come from, there is a great opportunity to provide the infrastructure. And I would actually like to warn the people in the CS world is that if you don't do it, others will do it. Don't try to be religious about I have to do it just because I'm the owner of that. It's going to happen no matter who is going to do it. There is a great opportunity to learn communities how to work together, and a great opportunity really to build what's going to be the next telescope for learning science in the future. And thank you for your attention. Non ti so.
Thank you very much. We have told only 10 minutes for questions.